And welcome to the last community meeting of the summer for Linkerd here. We've only got a couple days left in the summer, and that's my story. I'm sticking to it. It actually feels a little bit like fall here in Idaho, where I am. We've got a great agenda so far this month. We're going to be chatting a little bit about 2.9 and how that's going, what's coming in that, and when we can see it land. Then we're going to have a presentation on Linkerd and tracing, everyone's favorite subject, specifically making it work with OpenTelemetry and using ASP.NET to do the tracing itself. I'm super excited about that. While I love ASP.NET as a language, it's one of those I haven't spent much time working with, so I'm excited to see how that all comes together. Then we're going to have a presentation from one of the Summer Code students, Ali, who's been working on getting multi-architecture supported, specifically ARM, and making that run on Raspberry Pi so you can have your home lab running Kubernetes and Linkerd. I'm super excited to hear how that goes. In particular, I think that the individuals who put the tooling together for the build pipelines almost never get the credit that they're due. So I'm excited to hear about that because it's always challenging to get that going. And then as per usual, we'll have our Linkerd heroes and QA time, also known as Stump the Maintainers. So think about any Linkerd heroes you'd like to nominate along the way, and we'll get to that towards the end of the meeting. So without further ado, Oliver, talk to us about 2.9. What can we be expecting to see there?
Well, we've been working on 2.9 for a while, and we're still working on it. One of the big things that we're in the process of merging right now is a bunch of improvements for HA, especially in terms of how the proxy interacts with the control plane. So one of the issues that we had reported from one or two users a couple of weeks ago, or maybe a couple months ago at this point, was that if a node went down, the proxies could take up to 20 minutes to rediscover the control plane. And as we dug into that, we learned that this is all kubeproxy's fault. And kubeproxy can be pretty slow at detecting these kinds of failures and changing the service and how it gets routed. So we've redone discovery to be based on serve records so that we can do headless services, connect load balance directly to the control plane components. So that's been a ton of work, and we've got the proxy side of that done now, and we're working on the control plane side of it. One of the other big changes that we've merged probably since the last community meeting was that we've added the multi-threaded runtime in the proxy. And so what this does is if you give the proxy more resources, it'll use more threads, right? And so previously we would only use a single thread for the proxy ever, and people can hit scalability limitations and bottlenecks with that, especially on ingresses. And so if you want to give the proxy more CPUs to use, it'll happily use more CPUs now, and that's all landed. And we feel pretty good about that. And early reports show that if you're doing like high concurrency, heavy loads, tail latencies are much, much, much better. So we're looking forward to that. We're doing some benchmarks on that stuff presently.
Awesome. Anecdotally, I saw the proxy limit at about 10,000 RPS in and out. And so being able to use multi-cores means you can go up over that, which is pretty great.
Yeah, we're really excited about that. And then the other thing that we're still hard at work on is setting up for TCP MTLS. And what that's going to do, the way we're doing that is really changing how the proxy does discovery completely. So this will all be done per connection. As soon as the connection comes in, we'll cache everything, of course, but we'll no longer have to look at host headers and things like that to do normal routing, which will eliminate a huge class of both bugs and configuration gotchas and things like that. So really excited about that work, but it's a long pull, and that's kind of what's holding up the 2.9 release at this point.
And for those who are interested, getting to TCP MTLS because of the discovery changes will, knock on wood, also make it so you can use TCP for multi-cluster.
Yeah, we may scope that out of the first implementation. So we'll do multi-cluster support when we do server first protocols for this. And depending on timing, we may opt to do 2.9 without that feature so that we can get something out for y'all sooner. But yeah, all of that will happen soon. We're working on it.
Yep, definitely something that we're working towards. And then let's see. So something else in 2.9 that's landed to go through some of the summer code projects. We've got the service topology support in now.
What does that do? I mean, I kind of know, but do you want to give a little summary?
I will say the thing that I actually care about out of it,
yeah.
Which is the to get to service topology support, we needed to support endpoint slices. To give folks a little bit of background on endpoint slices, the way that a service works in Kubernetes is there's a single endpoint object that's tied to each service, and that endpoint has all of the IP addresses for your pods in it. So you could imagine a 1,000 pod service having 1,000 entries in a single endpoint object. The problem that you run into is that that endpoint object needs to be consumed by anything interested in endpoints. Linkerd happens to be one of those where we need to consume all of the endpoints so we can do routing. The more interesting one there is kubeproxy though, which means that every time a pod shows up or goes away, the endpoint object needs to be shipped to every single node in your cluster. Now, that's not that bad if you've got 10 pods, 20 pods, 30 pods, but once you get into the thousands of pods range, a single pod changing can cause massive amounts of bandwidth usage. Imagine this now being a multi-region or a multi-zone cluster and you're pushing crazy amounts of bandwidth everywhere. So endpoint slices are literally just chopping endpoints up into multiple chunks. So when an update happens, instead of needing to update a single object with 1,000 endpoints, it updates a single object with 100, which suddenly makes it be efficient. It's almost nothing more than a compression algorithm, to be entirely honest.
Right?
Yep, basically
and
right.
Actually, yeah, we've actually kind of preempted a lot of this stuff in our own APIs for a while now, and so we never send only on the first update do we ever send the full set of endpoints in a service to the proxy, and everything other than that is just diff based. Because for this exact reason, that with large clusters or large services, you really can't expect the whole set to update every time. And what service topologies do is give you kind of the means to have locality be expressed to say, I only want to use pods on the same node, and if they're none on the same node, I want to use them on the same availability zone, and so let you kind of build these hierarchies. But it's a pretty crude tool, so you should be careful with it.
I think that we're going to see how folks use it. In my opinion, this is a feature that Kubernetes core landed without much thought as to how users are going to interact with it. It's a great primitive, but to your point, it's a very crude primitive that doesn't work with the whole ecosystem. And so I'm super excited on it, specifically just to see how people use it, because I think that the limits there are going to be interesting, and that it's crude, it'll work. We're going to need to start to do more advanced solutions in the control plane discovery side of things, I think, which we now have the tools to do. So awesome. So that's service topology support. Another one of our summer code projects that's landed that we're actually chatting about later today is the ARM support specifically. So now you can run everything on your Raspberry Pi. I won't spoil later on because we'll be hearing a whole bunch about that, but it is exciting. Now you can have that pile of Raspberry Pis actually do something instead of just sit there in the corner and stare at you with the look of disapproval. Maybe that's just my Raspberry Pi cluster sitting in the corner doing that.
And then Mayank's been working on the conformance test suite, which is basically using Sonobuoy to start writing integration-like tests that let us, I know ultimately users kind of validate the states of their cluster with Linkerd and kind of make sure it's prod ready. But we'll be using that internally a bunch more before we unleash that on y'all.
But the general idea there is that while check is awesome, a lot of check is really only static. We'll go look at the state of your cluster and that's about it. Most of the hairy Linkerd issues end up when you actually start to run things. Like a really great example is in GKE private clusters, the GKE master nodes can't actually talk to the rest of the cluster without a firewall rule, and proxy injection just breaks silently, and you have to go figure out how to do it. And it's not something that we can test through check, because we can't just go create arbitrary resources and see how it works. And so the conformance test suite kind of is taking the next step towards everyone's Kubernetes cluster is a snowflake, and making the experience a little bit more reliable in the long term. But that is a good point, Oliver, and that this is just kind of something for us internally. The end goal is to make it blow out and have everyone use it, but we're still trying to get a feel for what it means to have a conformance test suite and figure out the rough edges there. This is definitely going to be a long-term project, one that I've been particularly excited about getting kicked off.
Yeah, it's the kind of thing like when someone says, oh, you know, I'm on this AKS, whatever, and we haven't run that before, that we can kind of point a standard set of work, like a standard workload and set of exercises on that cluster to validate that platform.
Yep. I mean, as a great example, everyone's CNI implementation is different, and it always requires a little bit of fiddling. And so having a conformance test suite to say, oh, yep, it's definitely CNI and it's busted is pretty useful for us. Awesome. And with that, I think we're done with 2.9. Oliver, do you want to go on record for a date that we're going to see that, or are we going to wave our hands and say?
No, I think it's probably at least a month out at this point. I think we're going to get at least 2 sprints in there, and we'll make the call at the end of the next sprint and see how close we feel like we are with this. Because there's a bunch of kind of heavy changes in here, we're going to be a little cautious in terms of rolling that out. But the next couple of edges that we are going to put out are going to start feeling a lot closer to that, and we're doing some cleanup. Like this HA stuff will, if not fully land on this edge, over the next edge, and you know, we'll be rolling these things out. So test edges if you care about these features, because that's the best way for it to get into a real release.
Definitely, and as always, throw the edge releases on your staging/dev cluster and play around with them, because that's where we go play around with new features and figure out how it all fits together.
Yeah, and I guess one of the things to call out there, which we need to put some docs on before the stable release, is that the add-on work that Tarun's been doing makes it possible to really turn off lots of Linkerd components. So things like the web UI, Prometheus, Grafana, if you don't want to run that stuff, or you want to run an alternate one, it's now getting easier to just turn that stuff off. And so, for instance, in my own tests, when I'm running Kine on my laptop, I don't want like 5 Prometheuses running. So I've been using all this stuff to strip it all down and just run, you know, tight tests or benchmarks, which is really nice. And that stuff will be landing in 2.9 for sure.
And I think that it's good to call that one out, and that's kind of again a long-term project that we are working on towards the multi-cluster and edge kind of solutions. You can imagine having a small install at a store, we'll call it a fried chicken store, and you wouldn't want to have the dashboard and Prometheus and everything running there. You really just want to have the small service mesh running so you can get the multi-cluster support. And it's all part of kind of opening Linkerd up for more interesting use cases. Ali's work is a really great example there. Being able to run on ARM means that it opens up a lot of edge style platforms there. Cool.
Yeah, one of the really exciting things coming up there, which is not going to be 2.9, but we'd love some community involvement in it, is making the proxy injector a little bit more flexible and generic. And so right now the proxy injector has to have kind of all the knowledge for how the proxy gets configured. You know, this is why folks have to add PRs to support new annotations so that we can set certain environment variables in the proxy. And really, we'd like to open that up so that it's a lot more generic. And you know, maybe you can even write your own webhooks if you want to do advanced configuration stuff. So that stuff's coming, and would love help figuring that out.
We definitely are in the phase now where getting help on good ideas on how to do that and the user experience and how it fits together would be greatly appreciated for sure. As always, go drop in and open up an issue, start an RFC, jump into Slack, chat with us about it. We'd love to have a conversation there. Okay, Ivan, you want to take the next section away?
It's going to be Charles, actually.
Oh, Charles, take it away.
Hey, good morning, everybody. Thanks for joining. Yeah, this is a very, very exciting community meeting. There's a lot of work that went on behind the scenes, so I have some nominees for my heroes coming up later. But before we get into that, I think the first thing we're going to do is jump right into our demo with Kelly Burr, who is part of the community. He was asking some questions and helping out in the Linkerd Slack. If you are not a member there yet, you can always join at slack.linkerd.io. And yeah, Kelly was helping out with some distributed tracing stuff, and he has a very his environment that he has set up is atypical from what we're used to in terms of distributed tracing. And so I was quite interested in getting him to chat with the community, other folks who might have a similar setup that are doing distributed tracing or are using AKS and .NET. So with that, I will let Kelly chat and show you what he's been working on. He shared a repo. I will put it into the chat Slack here so you can follow along. I ran through it last night. It was pretty great. So yeah, without further ado, let's get Kelly to share it with us. Let me unmute you. I don't think I have that power.
Okay, I'm unmuted. Can everyone hear me?
There we go. Yep, perfect.
All right, fantastic. So first of all, thank you, Charles, by the way, for the t-shirt, for the swag. Appreciate it. That's awesome. So yeah, we first of all, I'll introduce myself. Kelly Burr. I'm a head geek for the Dark Capital group of companies and co-founder for Upheaval. And that's where we ran into the atypical setup that Charles was talking about. Is we're using Linkerd in our environments, and we're building a records retention blockchain-backed solution where we wanted to be able to measure block writes in milliseconds and handle, you know, millions of transactions a second. And we've succeeded in doing that, and we're really excited. And we also really appreciate the help that the Linkerd guys have given us in, you know, getting through the ceiling on the TPS and stuff. But when you're doing that kind of a solution, when you're trying to get, you know, tens of thousands to millions of transactions a second, and you're trying to optimize for, you know, microservices-based API calls that need to be measured in milliseconds, especially when you're dealing with something like trying to write a block on a blockchain in milliseconds, being able to see what's going on in every component becomes super important. And that's what led us into the distributed tracing. And at first we were setting it up on our own, and then we found, oh, hey, there's a Linkerd add-in for this, and it interacts with the proxies, so we can actually see everything going back and forth. And then it was interesting because we're using .NET Core for this solution. And the Linkerd has, let's see, can I share my screen here? Will it let me? Yes, yes, let's see. All right, perfect. Let me show this screen. So Linkerd has on the website a great write-up on distributed tracing. And it's focused on the emoji photo sample. So anyone who's interested in it, I definitely recommend you start here at the Linkerd site. And again, that sample, that does link to a GitHub repo, and it's got sample code, and it's all in Go. And while Go is cool, and we all love Go, most of my days are spent in .NET and C#. And so then as, you know, as our group figured out how to make this all work with .NET Core code running in Kubernetes, that's what, you know, got us in, you know, and had me in the community kind of helping out when other folks were asking questions. So to prep for this, I put together a GitHub repo that's getting posted in the chat. I also posted it on the Linkerd Slack channel earlier that'll walk you through all of it and in more detail that I'm going to have time for today. But what I'm going to show you real quick is, you know, as I put here, it's an oversimplified but repeatable demo of distributed tracing using the Linkerd with the Linkerd add-on, which will give you Jaeger and Open Census Collector, and then using the Open Telemetry beta, which is still very much a beta in for .NET Core code in Kubernetes and diving into, you know, web APIs, gRPC, Redis, SQL Server, and actually seeing what's going on. So, you know, why would I want this? And obviously everyone can go through the repo. I know this is going to be hard to see on the screen share, but this is the kind of output, right, we get from the Linkerd distributed tracing. And so you can see in the examples here, you know, coming in all the way down through the service. And I've highlighted a few key things. You can see the screenshot easier, but, you know, total duration of this call was, say, 1.3 seconds. This is all based on my demo code and demo repo, right? We can see where it, let me actually zoom in a little bit. We can see where it, you know, the web API calls out to a gRPC service that was actually, you know, 879 milliseconds of the total 1.3 seconds. Inside that service, we can see that we had a cache miss, right? Where we, you know, went out and checked Redis, which was fast, only 8 milliseconds checking the cache, but we had a cache miss. So then we went and actually had to go write a record into Microsoft SQL. We can even get things like exactly what SQL statements were written. And we can see that actually the writing to SQL took 600 milliseconds, but a real interesting thing that the trace will show us here is only 180 milliseconds was actually writing the record into SQL in this trace. You know, the rest of it was just getting the SQL connection. So maybe we need to improve, you know, this tells us, hey, connection pooling is an issue for us here, right? So that kind of gives you an example. So I'm gonna close that down and kind of talk about how distributed tracing works. At its core, it's nothing more than adding these HTTP headers to the calls. And how you can get this kind of view is also in the repo, but really it's just adding these B3 headers, right? The trace ID represents the entire call. So that's the whole round trip from the client to the API from the outside. This, in my demo, actually gets injected by Nginx. The span IDs happen within the traces. Any given trace is going to have multiple spans, and that's what you saw in the demo. Every little section you saw there is a distinct span, and that gives you the breakdowns within your traces. The parent spans are how it correlates the spans to the parent. That's how you get that nice nested hierarchy. So again, this is just an example. This is based on a Google Echo headers container. I've got instructions in the repo on how to load this into a test cluster so you can see this output, but I just wanted to call out, there's really nothing crazy or magical about this. To get distributed tracing between HTTP calls, APIs, gRPC, which is really just HTTP2, right? It's just a matter of having these. And with distributed tracing enabled in Linkerd proxy, it allows Linkerd to actually watch for these headers when it's injecting and when it's proxying your requests, and lets it fill in there and lets it show you what's happening in the proxies. And that gets really interesting to have that additional information in there, in addition to the mods to your code. So real quickly, I'm going to go ahead and pull up some code, and let's just run the sample, and I'll show you what this is going to do. So I've all the code here. I pulled it up in VS Code. In the repo, I did include a solution file for those who prefer full Visual Studio. It's what I use most of the time during the day, but these samples will all work in VS Code also on any platform. So I'm just going to go ahead and run my sample code. And this sample code does nothing more here than call the APIs and say hello to John, Paul, George, and Ringo, right? And so looking at the output here, we can see, great, we said hello to John. Took 5,000 milliseconds when we first, oh, sorry, that was an old run. So when we say hello to John here, 671 milliseconds to say hello to John. Paul was 54. George 50, Ringo 54. We said hello to Paul again, because out of all of them, he had some of the best solo work. And that takes us, this was down to 41. We tried to post an empty and we got a bad request. That's expected, right, from input validation. We also tried to say hello to Mud, and we also got a bad request. Well, that's unexpected. So let's go take a look at our traces, because that was all tracing. So all I'm going to do here is pull up my Linkerd dashboard. Right, and I've got the Linkerd tracing add-on installed. I'm going to go into my demo namespace here, and I can see it's, you know, meshing and showing me my services. And well, I've got 100% success rate here. But let me see. Let me hide this panel here. There we go. And with that add-on added, I've got this awesome little Jaeger symbol here. So I know this was all coming into my Greeter web API. I'm going to go ahead and just click there. And that's going to pull up all my traces. Now, it's going to pull them up latest first, which is really convenient, because what I want to see the most is why saying hello to Mud failed, right? So I'm just going to go ahead and click this trace. You can see all these spans here. And I can also see a really cool chart here of showing me how long this stuff took. So let's go ahead and check out this span. It shows me my gRPC service had 1 span. My web API had 4 spans. Linkerd proxy gave me 8, and Nginx gave me 2. So let's go ahead and look at it. I mean, this is a pretty valuable view, right? And so what it's showing me here, again, I come in through Nginx, which is my ingress for my controller. And then, you know, Nginx processed internally. Nginx, I'm admittedly not entirely sure why Nginx gives me 2 spans. You get 4 from the Linkerd proxy. That was confusing at first. And, you know, thanks to the guys for explaining this to me. You go out from the Nginx pod into the web API pod, back out from the web API pod, back into the Nginx pod. So you actually get 4 traces here. And we can see these where they're inbound, outbound, right, on all the traces. There's the inbound traces, here's the outbound traces, right? And the reason the outbounds show up first is the outbound, you know, coming back in this is the longest trace, right? So then we get down here into my web API. Web API took the post to API greeting, you know, no surprise there. It called the gRPC service, and I can see, because I'm annotating, I'm adding to my trace, I can see, well, this is literally the JSON representation of the protobuf it sent to the gRPC service. We can see this activity automatically created as part of the instrumentation. I'll show you guys in a minute. We sent the HTTP request out. Okay, that's all good. We've got now the Linkerd proxy showing me the traffic going here. And we can see that going between nodes in the Kubernetes cluster is taking me about a millisecond, right, total in the proxy. We got to my gRPC service, and then it died. It stopped. Why? Logs. Well, I've got an invalid argument exception. So apparently there's some validation in that code that's logging your name is not mud. So that's why the gRPC service is kicking that out as an invalid argument. So now we know why that call is failing. And if we want, we can go back to the code here in the gRPC service, and we can see exactly what it's doing there. And let's see. Oh, yeah, right there. If name equals mud, send a stat, you know, give me an invalid argument. And then I got that in the traces is as easy as this piece here, this activity current add event. And I'm just, you know, adding that event here, so that will show up in the traces. Okay, cool. Also, if you're interested in how on the web API, how I added all the parameters there, it's really pretty easy here. I'm just starting an activity, and I'll, again, talk about this in just a second. I'm just literally tagging on my RPC request and RPC apply here by writing those out. Now, and, you know, obviously not usually appropriate in production, but for the sake of the demo, it, you know, shows you real easily what you're doing. But this is really all that's required in your code to get all these spans and tracing in the code. So let's go back here, and I'll show you, you know, let's go here to the long one. Let's see. Internally. Also, by the way, you notice my timings here are a lot shorter. That's because this is just talking about from when it hit Nginx to when it went back. So, you know, looking here where it said that St. John took 671 milliseconds, or sorry, that's the wrong run. Took, you know, Paul took 54. It doesn't take that long inside the cluster. Part of that is transit, because this is all running in an AKS cluster. So let's, you know, look at an example here. This should be Ringo. Great. So here's the span. This one went a lot further. We can see where we're checking our cache, inserting our records into SQL. Right, and open telemetry, execute. You know, we can see where we're getting the actual SQL commands running. Also, a real fun one I've added here is I'm recording my record ID I get back from SQL. Super helpful if you've got a data inconsistency you need to trace down. We've got round trips to Redis in here. And so here you can see, again, it going all the way through the trace, showing SQL, showing Redis. We had a cache miss here, right? So we have a cache miss searching for Ringo. If we go back here into this one, we can see there's a lot fewer spans here in the gRPC service. So why was that? Well, when I check the cache, I got a cache hit, right? So looking in my gRPC service, well, this is how I'm checking that, right? I'm just starting an activity called cache check, putting the search key in, right? Because you can see my search key was Paul. And then if I get a hit back from Redis, I'm recording cache result hit and returning versus recording miss, and now going back to inserting my SQL record. So that's a little bit about that. Now, how do you add that to your .NET Core code? So we'll just start here, gRPC service. So first of all, you need to know where to send the telemetry. It's all here in the repo, but this is where you send it to the Linkerd connector, or Linkerd collector, which is Open Census Collector that gets installed with the Linkerd add-on. And really, the only interesting parts of my repo, besides just some of the code here in the service and the controller where I'm doing my own thing with activity, the only real interesting part is here in startup. And this is kind of what I wanted to show you. This is how you add open telemetry to your project. So obviously you've got some NuGet packages to add. You can check out the repo for the details there, but this is, writing to the console, writing to Zipkin. This is what's important, the Zipkin exporter, to get your traces to Linkerd. And then the ASP.NET Core instrumentation, and then I added SQL Client and Stack Exchange Redis because I thought it would be cool to include those in my traces. Again, optional for how you want to do it. So startup, again, all in the repos, but there's a couple of really key things I wanted to show you on how to get those Linkerd spans in here and how to make it work with Nginx. And it's actually this little bit here. Okay, so .NET Core by default uses W3C headers, and as everything that the WC3 decides to adopt as a standard, they do it a little bit different from how everyone has done it up to that point. They always seem to have to make it their own. Cool, good for them. I'm sure that will catch on. And at some point, I think Nginx has support for W3C headers now. But the B3 header format is really that Zipkin standard, that default. And that's what the Linkerd proxy supports, and is fully supported by OpenTelemetry Beta. So here in my services, there's a couple of real key things that you want to look at. One, I'm adding an activity source. Program.name here it's nothing but a constant that I put in just because I want to use it in a couple places, right? Oh, sorry, let me go back to startup. So I want to add an activity source and add that to as a singleton in my DI, right? And then when I add my open telemetry, I add an activity source, right? Based on the name of that activity source I added. Then I'm going to my config right here to say what's my tracing format I want. Again, the default, if I don't specify this, is W3C. I want B3. Now I'm calling it B3M versus B3S because the flavor of B3 that we're using that comes from Nginx is multi-header, where they're all split out into those 4 or 5 different headers I showed you. B3S, they cram it all into one header with delimiters. So my app settings here set up for tracing format in production is going to be B3M, right? Oh, not what I wanted. I want to go back to startup. So basically all I have to do here is when I add the ASP.NET Core instrumentation, this is what automatically reads the spans that come in from Nginx and pass through the Linkerd, do get picked up by Linkerd automatically. This is what tells it, hey, rather than WC3 headers, I want B3 format where single header is set to false. So that will cause, doing this here makes ASP.NET automatically create activities with all the appropriate traces for your inbound activities. If you do only this, you'll get a top level activity. No magic here, right? This is just saying, okay, I also want to see SQL client and I want to see stuff that happens with Redis. Okay, this is, having the console tracing is really nice when you're running in your own debugger. Exporting to Zipkin here is just how I say, great, go ahead and send this stuff to the Linkerd collector so that Linkerd can collect all this, get it into Jaeger, and we can show it there. And that same thing, service name equals program name. Again, just needs to correlate with my activity source so that everything will match up, and then I give it the endpoint. Okay, so this is on my gRPC service. There's one additional step if you're calling out to other services. The gRPC service just uses SQL and Redis. It doesn't make other service calls internally aside from those. In my web API, I'm doing all the exact same things here, but then I'm also adding this. I don't need the SQL or Redis here because it's just calling gRPC. It does the same Zipkin and the same console tracing, but this bit here and the order here does matter. The .NET gRPC client uses HTTP client internally. So I need to inject the exact same thing that I had for the inbound requests to my outbound HTTP client to tell it to send B3 headers. And then I chain onto that, add gRPC client instrumentation, which will inherit the instrumentation from HTTP clients. That way, outbound HTTP and gRPC calls to other services in the cluster will send B3, allowing Linkerd to pick those up, right? And then that's where you see in my, in the greeter, that's why my greeter gRPC is telling it wants to take B3 in, because it's actually not Nginx. Nginx is going to be sending to the web API. The web API is going to be sending B3 to the gRPC service. So anyway, that's the sample. That's the key. I know I talk quick. Obviously, if let's see, I can probably stop sharing. So I don't know if anyone has any questions about that. Also, I'm on and off. I try to be in the Slack channel, the Linkerd2 Slack channel, as much as possible. And I'm happy to answer other questions and take a look at stuff there. Those of you who do notice, if you do read the repo, you'll see there's a little Easter egg. There's actually a bug. There was a bug in the OpenTelemetry APIs, the Redis instrumentation, that caused the sets to appear in the wrong span. They actually just merged my PR in last night. That'll fix that. So if you notice that and you're like, wait, that doesn't look right. No, it's not right, but that's fixed now. So anyway, OpenTelemetry is a beta. It is changing, actually. If you were to go pull the code from their trunk right now, my sample wouldn't work. My sample code works with the latest released NuGet packages. They've changed some of the method names. They're still making breaking changes. But it's a really good package, works really well, and it works awesome with Linkerd. And yes, you can set up Open Census Collector and Jaeger manually, and that'll work just fine. I really like it with the Linkerd add-on because the integration with the dashboard is awesome. To be able to see my traces, see my HTTP and TCP stats, and then go see all my, be able to actually go look at my spans in Jaeger. It's hugely valuable. And again, when we're trying to, build services that have millisecond round trip times, there is just no substitute for this kind of capability. So anyway, I'll say back to Charles, unless anyone has any questions.
Yeah, that was super awesome. So there's so many things to unpack there. Really appreciate you sharing that with us, Kelly.
Sorry, I went about 10 minutes longer than I planned on.
Well, information, it takes time to get this stuff. So I'll be brief here. I really liked seeing the action in the code. When I've talked with folks about building distributed tracing with Linkerd, I do a little bit of hand wavy stuff and say, and you have to add the library to your code in order to get these traces, but to actually see it in action is super cool. So, so yeah, that's really awesome. Thank you so much for sharing that with us. In light of, and so if y'all have questions for Kelly, please put them in the Linkerd Slack or in the chat. But yeah, it's really, really cool stuff. And I encourage you to play with the repository as well, because there's good stuff in there. With that, I think we will hand it over to Ali, who's going to tell us about running Linkerd on ARM architectures on a Raspberry Pi, which mine now, Thomas, is also no longer angry at me. I had to put some new fans in it because they were very noisy and my wife did not enjoy that. So, but now I've got Linkerd running on my cluster. So please, Ali, share with us your experiences and everything that you did with building Linkerd for ARM.
Okay, thanks, Carlos. I hope you can see my screen now. Is it available? Yes, I think so. Okay, cool. Hello everyone, I'm Ali. Today I will present my GSOC project building Linkerd for ARM, and I'm mentored by Charles. For those who doesn't know what is GSOC, it's a Google program to introduce a student to open source. Okay, so yeah, this is me. I'm currently pursuing my master's degree in software system engineering at RWTH Aachen University in Germany. Okay, so the agenda for today is to start with a bit about what is multi-architectures or multi-platform and why it matters. And then we continue to how this project is accomplished. And the last part, if we still have time, we could do some Q&A if there is some questions or any doubt. Okay. Start with the multi-architectures. The terms, it basically refers to a different CPU design, and this design is different is because they have other purposes or goal in mind. For example, the typical machine architecture is the x86, which is mostly used nowadays in our laptop, our PC, and cloud instances. Traditionally, they are designed to have a peak performance, therefore they consume more energy. On the other hand, for example, ARM is having a more simple design, and therefore their energy footprint is considered low and is more common in small devices like our phone or tablet. And there's also more architectures like PowerPC or IBM S390, and yeah, there's others too. Why ARM specifically? It is because the users are increasingly growing and demanding it. It's already on Raspberry Pi, IoT devices, and also recently Apple decided to use ARM on their future MacBook. And the idea is by supporting more architectures, we can broaden the market and use cases like in the edge computing with IoT devices, small home lab with Raspberry Pi and K3s, for example. And yeah, there's a lot of more that we can do in there. And this is not only for ARM, but also for other architectures. Okay, now we are going to explain how we do this project. So basically, Linkerd is released as a Docker images and also a CLI applications. And these three repositories are their main repo, basically. There's a proxy init repo that contains IP table rules to redirect the traffic. And there's also Linkerd proxy repo for the data plane and the main Linkerd repo for the control plane. Okay, so the initial plan was to build the images one by one for every architecture, push it, and then manually create the manifest to connect between those images. We also send a build argument, which contain the target architectures to Docker file, so that later can be used for cross-compile. So yeah, the cross-compile part, fortunately that we use Go and Rust in our code, and it's already provided built-in features to perform cross-compile. For Go, for example, we can just set the environment variable as a Go arg to the target architecture that we want to build the binary for, and we use this value based from the build argument that we passed in the previous slide. And similar also with Rust, we built with the extra options, minus target, and then say the target architecture that we want to build. Okay. And after more research, I found other options to build the multi-architecture image by using a new experimental features from Docker called BuildX. This tool is basically a wrapper on top of BuildKit, which give us more features like advanced caching, concurrent build, and now with BuildX is a multi-arc support. And the solution is like the preferred way that Docker encourages to build the multi-architecture images now. So in this sample command, it's look like a regular build command that we usually use. The difference now, we can specify the platform in one single string separated by a comma, and then we can just specify all of the architectures that we want. And this means that we are going to build Docker images for these three architectures, for example, in this command. And there will be a 3 separate concurrent build processes running when we do this. And the -- push command is for pushing the images to the registry directly. And this one is unfortunately mandatory if we build multi-architecture images using a BuildX, because there is current limitations that BuildX cannot load this to the normal images, images repository in the local. And then, but if you only use a single architectures, like only build one single architecture, it will be fine. And then you can use it without push, and we can use a -- load to load it normally to the local Docker images repo. So yeah, by using BuildX, it is possible to build the multi-arc images with these 3 options. The first option is using QEMU, which is an emulator to run a foreign architectures instruction set. And this option is the easiest one and most straightforward because it's but the problem with this is considerably slow. The second option is to use a remote machine by provisioning a target machine, in this case, ARM machine. And then the BuildX can be set it up to connect with that remote machine to perform the build remotely. And this is obviously fast because the build happens in their native environment of the target architectures. But then we need to provision the machine and manage this machine. The third option, and this is the option that we use currently, is using the cross compilations. And this option is relying on the language compiler to perform the cross compile, but the good thing is we don't need to set up any remote machine. Another thing that some features that come with BuildX are they are using the target platform as the source when there is a from command inside the Docker file. So every time there is a from command, it will be based on the target platform. Also, there is some default argument that is automatically available inside the Docker file. And this is going to be used for cross-compile purposes. For example, in this case, we're performing a cross compilation in Go. We can use the target arc arguments, and the value of target arc is the architecture that we specify when calling the BuildX command in the previous slide. And for the case of reusing images, we can pull specific images using -- from and utilize the build platform argument. In this case, it will reuse the same image and not to try to pull the image on every target platform that we specify. And this is currently the solution that we use for cross compilation and reusing the image. Another benefit that also, besides performing the multi-arc images by using BuildX, before we are relying build by using a private remote machine to make a build faster in the main repo. But still then on the fork repo, this remote machine are not accessible. So therefore the build happen from scratch and the CI takes a long time. And now with BuildX, we utilize the caching mechanism so that every time the CI process build images, it will create a cache and upload the cache as an artifact. And this cache will be shared, and even the fork repo also can use the same cache as the main repo. So in the end, we ditch the need to use a remote Docker machine and solve the slow CI process in the fork repo. Okay, so now the current status of the Linkerd already works on ARM since Edge 28.1, and you can start to try it by installing the Edge versions, and also it's possible to check the published images by running these commands. Yeah, I will just share you later. Okay, and the challenges during the project is the testing process is relying on the external resources. In this case, is GitHub Actions, the CI system that we use, and I cannot test it in my local. So the only thing that I can do is pushing my stuff and then wait for the CI to pick it up and then processing. And then I need to repeat this process with committing and waiting, this kind of thing back and forth. I also work with multiple repos and that are interconnected each other, so that I need to think and be more careful while making changes relating this thing. Yeah. The last part is, even though the main project itself are already completed, which is supporting ARM architecture, and we already did officially, and there is an extra task that I'm still working on, that is adding the ARM integration test to the CI system. So yeah, that's currently what I'm doing, and basically it. Thank you.
That's great. Thank you.
Yep. Nice work, Ali. And
like,
again, oh, sorry, go ahead, Oliver.
We're like slowly saving the environment by now supporting ARM.
Yes.
Yeah, we had a conversation yesterday. One of the neat use cases is it's something, again, that I learned as part of this process, is this Industry 4.0, doing things on like computing at the edge and Internet of Things, where this could be really relevant and I think pretty useful, especially if you need a service mesh out there. So thank you, Ali. Thank you for all your hard work. You did a great job, and your continued work on the integration test. So I could keep rambling, but I know we need to keep moving on. So I will hand it back to Ivan.
I think it's back to Thomas.
Back to Thomas.
Don't hand it to me, Thomas.
Oh.
Okay, I have a trivia question though. Let's see if anyone knows this. In Kelly's demo, he was talking about the B3 header. Does anyone have any idea what B3 means? You put it in the Slack if you do. It's kind of funny. Okay, so B3 stands for Big Brother Bird. Big Brother Bird is the original name of Zipkin before it was open sourced, when it was a Hack Week project at Twitter. And so Johan, who is, I think, at Slack now, wrote the initial version of Zipkin called Big Brother Bird. We got those headers written into Finagle. Zipkin was open sourced, and they never changed the header. So we're stuck with B3 forever. Hack Week project, yeah.
Except for those WC3 headers that
we'll never use
land someday. Okay, I think presentations went a little long, so we're going to have to skip our normal end of the hour stuff. Thank you, everybody, for coming. We appreciate it. As always, jump on into the Linkerd Slack channel, and we can answer questions and do some brainstorming, help out. Extra thanks to Kelly and Ali for presenting. Thank you so much. It was super interesting to see your use cases and what you've been up to. And on that, everybody have a great rest of your day.
Yeah, talk to you in a month. Really good job on the demos, everyone. It was awesome.